Johnson, this is Priya, Chris, Steve, and Adekunbi. Our team's Team 11 SoundMakers. Our customer is Professor Robert Kotiuga. And our project is building an auto-tuning guitar. It's a self-tuning electric guitar that's a travel-size guitar. That means it's headless, and the body has a pegs inside the body. So therefore, we're building an enclosure to have all the circuits inside the guitar. Our system is basically a feedback circuit, which compares the frequency of the plucked string and compares the frequency that's already stored in memory. Therefore, basically, I just pluck a string, the frequency is sent through an amp and a filter circuit that cleans the noise, and it compares it to the stored frequency depending on which setting it is and which string it is. When it's compared, it'll send a signal to the motor to turn it to the left or turn it to the right. And next is Priya.
This is our block diagram. Again, the input comes from the guitar pickups mounted directly on the guitar body, goes through the filter circuit, signal is amplified and denoised, and then that signal goes into the microprocessor, which again is powered by a 9-volt battery. Easy user interface, sends a signal over to the servo motors and turns the tune pad accordingly. The beginning of the system starts with the input amplification stage. If you connect the guitar pickups directly up to the oscilloscope or into the microprocessor chip, the signal is noisy, the frequency is unable to be identified, so it needs to go through a filter circuit that can amplify the signal as well as denoise it. Depending on which string is being plucked, the frequency can range between 60 and 400 hertz. We defined our input voltage to be to be 3.3 volts. The circuit was designed 6 circuits for each different string. You can see there's a high-pass filter over here, forms a closed loop with ground that blocks any high frequencies. We have a second-order low-pass filter that blocks any aliasing issues that might occur in the A to D converter. Again, the op-amp swings from rail to rail. We recreated that situation with VCC as a positive rail and ground as a negative rail, and so VCC over 2 acts as a ground. We have the 2 47-ohm resistors, which act as which create a virtual ground for the circuit. And with that, the signal is able to be identified by the CPU.
All right, so in order to implement our filtering amplification and power supply designs, we utilized the Altium electronics design software to create our PCB. And basically we started with our filtering circuit schematics, and from after some error checking, we transferred that design into the Altium PCB layout editor in order to place our physical components on the board. Our finalized design is a 3-inch by 3-inch PCB that plugs directly into our main development board via a 3 by 32 pin header here. Basically, the way it works is the analog signal comes in here. It's filtered and amplified here, and that analog signal is sent out that 3 by 32 pin header to our main development board for frequency identification. From there, the appropriate EWM signal is routed back through the board and into the motor boards here. This is also the power supply for the motors, which are running 6 volts.
So once the signal comes in through the filters, it arrives to the analog to digital converter. We're using a 12-bit ADC, which has about 4,000 different points in the range from 0 to 2.5 volts. And how we're doing it is we convert it directly from the bit to a number that corresponds to millivolts, and it's accurate to within half a millivolt. And we're counting, constantly checking, and so we see if it ever goes high, then we know that we're waiting to see where it goes low. And rather than trying to look at exactly when it crosses zero, we just infer that in the time between that there's a zero crossing. So how we're doing it is we count the number of zero crossings in a quarter of a second, which is kind of an amalgamation of as trying to get as quick as possible, but still having an accurate signal. And it holds that value, and then it has a number for the frequency, the amount of ticks, the amount of zero crossings in a quarter of a second. So once it has the frequency in this value, it will send it to another part of the code, which Johnson's going to talk about, controlling the motors.
So we have 6 motors, which is outputted from the microprocessor. These motors are servo motors. They're continuously modified. Therefore, they can spin continuously upon past 180 degrees. The motors are controlled by pulse width modulation. That means there's a duty cycle, and no matter what the duty cycle is at 80 degrees or below, if the duty cycle is lower, it'll change one direction. If the duty cycle is higher than 180 degrees, it'll change the other cycle. So no matter how you modify the duty cycle, it doesn't matter for that. So for the program, there's a function which controls each of the settings. The function stores each of the frequency for all 6 strings for 3 different settings, and it compares it after I receive the value from C. Other part of the coding. The last part of this is that since the human hearing is within 5 cent, that means there's about a +1 minus hertz difference that you can hear a different in the tuning of the string.
Now for the user interface of the guitar. We wanted something simple for the user to have the user interact with the guitar to turn on and to choose a tuning. So the first step of that was creating a control knob, and that control knob was made using a rotary switch. That rotary switch allows the user to choose one of 3 different tunings that we set up for the guitar based on what a guitar user would need for most songs. Those tunings are drop D, standard tuning, and open G tuning. There's a 4th setting on the rotary switch which is off, making sure that when the tuning system is first initially on, you're not accidentally tuning to a string that you don't want it to be tuned to. That brings me to the on and off switch, which is an LED illuminated switch. Simple for the user to turn on and off, and it also indicates to the user when the system is on, so that they are not attempting to play the guitar and it's actually tuning when they do not want it to. The control knob and the on and off switch are both mounted onto the enclosure of the guitar. And speaking of the enclosure of the guitar, it is constructed using plastic sheets of Lexan. And those sheets were bent to custom fit the guitar shape. Because the guitar shape was not uniform size, we had to use these plastic sheets to make it. These plastic sheets of Lexan were also used to mount the motors into the guitar body. And that ensures that the motors are secure when they're turning, so there's no shaking or moving of the guitar, and all of the power in the motor can be utilized. To also ensure that there's no shaking or backlash in the guitar, adapters were manufactured with the help of the mechanical engineering department. And these adapters are custom fitted to the motors and to the tuning adapters on this guitar. And it makes sure that when the motor turns, it is securely attached to the tuning pegs, and there's no backlash either way it's turning. The user interface, which consists of, as I said before, the control knob and the switch, are also attached to the back of this enclosure, and the PCB and development board are attached to the top of the enclosure upside down, so that the motors and the wires from the user interface are easily attached to the PCB and the development board. As you can see in this picture, the user interface here on the back of the guitar consists of the on and off switch, the LED illuminated on and off switch, and the rotary switch, the control knob. And the knob used there is circular.